Let's look at the most favorable conditions and the simple model. So let's dig into this very simple scientific model. At least let's begin looking at how we can develop it. We're going to develop a scientific model about a simple cell forming. We're going to focus solely on the energy aspect. We're going to use the most favorable conditions imaginable. We're going to use real-world measurements where possible, and the real-world measurements will ground this simple model in reality. We want the analysis to be as simple as picking a green ball from a bag of colored balls, and I'll be using that metaphor throughout. That way we can't misinterpret the data. If it's that simple, then it won't be complicated in understanding. The basis for this scientific model comes from a book called Energy Flow in Biology. It's by a gentleman named Dr. Harold Morowitz. I am not going to reproduce the entirety of that book or even dig into the justification for what he says. I would recommend you purchase the book, you read it if you are interested in critiquing this. I do, however, produce his assumptions. If you want to understand the assumptions of this simple scientific model, then please go to section 3B, which is an appendix, to review those assumptions. So let's get an overview of this simple scientific and mathematical model. Now, I had mentioned in section 1.2, module 1, that math can't be applied to biology. So how is it we're able to have a simple scientific and mathematical model here? And if you see in this picture, there are actually three disciplines that are involved in this. There's physics, there's chemistry, and there's biology. And where all three of those intersect, that's where we're going to develop our mathematical model. That model will incorporate mathematical formalisms from physics and chemistry, both hard sciences. The contribution of biology is to provide the measured data, the empirical information that is plugged into the model. So this is how the model is grounded with reality. The model's values are biological measurements. I don't want you to be concerned that math is involved. This is going to be really simple math, so you should feel comfortable. So physics is used to describe the thermodynamic energy needs. Chemistry describes the processes and chemicals that are involved. Biology provides empirical data from actual live cells. Our scientific mathematical model is built at the intersection of all three of these disciplines. So what is the general best case approach? Well, we recognize that living systems share common chemical features, and this is to reduce the scope of the analysis to make our model simple and yet helpful by making predictions about the real world. We'll use a simplified system model as the cell. If you look on the right, we have the dead cell at the bottom and the living cell at the top. We're going to use empirical data to calculate the chemical energy difference between the energy level of the simplified living cell and the energy level of the normal dead state of the chemicals. If you look at the figure, the battery is intended to represent the dead cell being energized and becoming a living cell. We're going to calculate the probability of that energy gap being filled. And then we're going to compare that probability with other probabilities with the goal of having the nonsense detector look at that comparison and determine whether it's nonsense or not. I would recommend you go to section 3A for a primer in probability and its interpretation. If you're a little rusty, very simple math is all that's needed. So what is the best case? Let's take a very large batch of the simplest cells. In this case, we choose a living cell, Mycoplasma hominis, H39. The best case here is that it's a simple cell. You start with no impurities in the mix. You have no chemicals that might affect negatively any sort of reaction. You raise the temperature of those cells to break the cells into their raw atoms. For example, raise it to 10,000 degrees Celsius to break all the chemical bonds into the atoms. So the atoms are just high in kinetic energy, they're bouncing around. But this is also a best case situation because here we've charged up the chemical energy, the chemical battery, so that as the temperature lowers, as it slowly cools to 30 degrees Celsius, chemical reactions will form, bonds will be made, molecules will be created. And because we're slowly cooling the system, we achieve steady state with no disruptions. The alternative would be you start at a high temperature, you go down, then somebody adds energy to the system, so the temperature goes up and down. So we're not talking about an oscillating temperature. It's just slowly cooling. Then we allow the system to age indefinitely at this temperature. So we have unlimited time with no disturbances, again, a best case. We create compartments the size of the original cells. So think of a box that is the size of a cell. And all the compartments have the elements to form a cell, best case. So every box has every single chemical from the periodic table needed to form that cell in the right amounts, right? There aren't any missing amounts of chemicals. There isn't an overage of any. It's the best case. And the compartment walls are impermeable to matter, but conduct heat. That means that the chemicals don't mix. By conducting heat, it means that everything will slowly move to the same temperature, so there's no chemical interference and uniform temperatures. Again, a best case condition. Now we're going to calculate the best case probability of life. We're going to call that the variable PL max. So P means probability, L means life, max means the best case, the maximum probability. And that's the probability of a cell becoming alive by adding energy with all the right chemicals in place. Again, it is the maximum best case probability. Just from an intuitive perspective, if PL max is more than 1%, then we should see life popping up all over every day. We should look at a body, a puddle on the ground, and we should just see pop, 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 cells forming. But we don't see this, so it should be much less than 1%. In fact, we don't see cellular life popping up at all. It's not being observed in nature. So PL max should be really small. But how small should that probability of a cell forming be? We're going to use a little algebra here. And what we see is each possible state of those compartments may be in the I state have an energy epsilon I. Now, just a refresher here, that funny symbol epsilon I, this is intended to be algebra. That's just intended, epsilon designates the state, and I is, in some case, the number. You could think of that if I have a set of balls numbered 1 to 10, I represents the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that the probability of the system being in that I state at equilibrium is then this equation. So in this equation, what it's saying is the probability of being in state I, that's the top of the equation, divided by the probability of all states. This is similar to picking the green ball out of a bag of red balls. The green ball would be the number of green balls on the top, and the bottom would be the number of all the balls. That EXP is normally just shown as the letter E. It's commonly known as Euler's number. It's used a lot in science. Just the bottom part has the Greek letter sigma in front. That's that sort of M on its side. And that sigma represents adding up all of the possible values. So this forms the equation just like picking a green ball out of a bag of red balls. Now, this equation is a little more complex. In the past equation, we were just looking at a single state, like a probability of a single green ball in a bag of red balls. In this case, what we're looking is all of the good states. A good state is the case where there's a live cell divided by all the possible states, meaning all the states where there could be a live cell. They're just as dead chemicals. The numbers by sigma on the bottom say j equals 1 to n. In the numbers on the sigma on the top say I equals m to n. What that's saying is there's a point. That point is where life is not possible for all states that have less than epsilon m energy, where epsilon m represents the minimum energy for a living system, which is higher than the basic chemical energy. So another way of saying this is that there's a cutoff point where below that energy level life doesn't exist, and above that energy level life does exist. And there may also be another cutoff point, but it isn't necessary, where the energy is too much and it destroys the cell, kind of like the grenade being pulled. That's an energy injection, but it's too much. So this again is like a probability calculation where you don't have one green ball in a bag. You have 10 green balls in a bag of 100 red balls. So the top part would be the 10 green balls, and the bottom part would be the total number of balls. And you're trying to calculate the probability of picking a green ball out of all the balls. But these epsilons are sort of mysterious, and this is where we ground it in reality. Biology can provide reasonable estimates for epsilon I and epsilon m from measurement data. Let's choose Escherichia coli as an example. It's a cell that contains 2 times 10 to the 10 atoms, it's estimated. Here we have epsilon m, which is the estimated living chemical energy, is 7.482 times 10 to the 10 electron volts. Epsilon 1 is the estimated non-living chemical energy, is 6.936 times 10 to the 10 electron volts. That difference is 0.546 times 10 to the 10 electron volts. That's the additional energy that this model would use for this particular type of cell to move from its lowest energy level, which are dead chemicals, to moving to the state of a living state. And PL max, which is a maximum probability, is 10 to the negative 100 billionth power. The best case probability, just looking at it from an energy perspective, of this simple cell forming is 10 to the negative 100 billionth power. Now that's a strange number. We don't normally see those numbers every day, and we're going to explore how to understand that. From the book, I've taken this table, and it lists out various different cells or viruses that exist and what the simple model would tell us about the probability of that forming, just based on the energy difference between dead chemicals and living states. We're going to focus on Mycoplasma hominis, H39, which is the small cell that has 10 to the 9 atoms. And its probability of it forming, PL max, is 10 to the minus 5 times 10 to the 9. So the simple model's probability estimate of forming a simple cell, from that table, it is 10 to the minus 5 billionth power. And again, this is estimated based on the initial chemical energy. Dead chemicals need to become a living cell.